Today we are going to discuss work, energy, and power. Remember, work involves the amount of force exerted over a specific distance. Work is not related to time. For example, if two winches lift identical weights, the same distance, they do the same amount of work, even if one winch takes longer. But in order to do work, it does require energy. Power involves time, force, and distance. Two winches, one slow and one fast, do the same amount of work to lift a given weight because they use the same force and cover the same distance. Time is not a factor, but to cover the distance faster, the faster winch uses more power. So what is energy? This is both a simple and a complex question to answer. Energy is everything, and it is often described as the ability to do work. Almost all food energy comes originally from sunlight. The chemical elements that make up the molecules of living things pass through food webs and are combined and recombined. At each link, some energy is stored, but much is lost along the way in the form of heat into the environment. When we eat food, our body uses chemical energy embodied in the food to move around. When we switch on the TV, electricity in the form of kinetic energy is used to create the picture on the screen and the sound. Most of the electricity produced in the world comes from the chemical energy released in the burning of coal, oil, or gas. Every time something gets warm, cools down, moves, grows, makes a sound, or changes in any way, it uses energy. The conservation of energy is a fundamental law of physics and chemistry, stating that energy can neither be created nor destroyed, but can change form from one to another. And it's the basis of the first law of thermodynamics, which we'll discuss in greater detail when we get into section 1.3. This conservation principle also applies to many other fields, such as in electronics through Kirchhoff's voltage law, or in fluid mechanics by Bernoulli's principle. Science classifies energy into two categories: kinetic or moving energy, and potential or stored energy. Potential energy has the capacity to do work by virtue of position or configuration. Examples of potential energy include gravitational potential energy, such as lifting an object away from the Earth's surface, gives the object gravitational potential energy because the object has moved against the Earth's gravity. Elastic energy, such as stretching a rubber band, gives the rubber band electromagnetic potential energy because the rubber band's molecules have been forced apart, overcoming the molecule's electromagnetic attraction. Electrical energy, such as applying a voltage to a conductor, gives the conductor electromagnetic energy because the electrons have not yet given in to the electromagnetic force. Chemical energy, where the electrons and molecules of fuel have electromagnetic potential energy because they have not yet fallen closer to the nuclei of the product that can be formed during combustion. And thermal or heat energy, such as changes among solid, liquid, and gaseous states, are electromagnetic potential energy because the molecules have overcome the attraction between electrons in one molecule and the nuclei of neighboring molecules. Kinetic energy is known as the energy of motion because it involves the movement of objects, which can occur anywhere from at the atomic level to that of a whole organism. Examples of kinetic energy include electrical energy, such as the movement of electrons in a conductor as they respond to an applied voltage, or even in thermal or heat energy, such as the movement of molecules and electrons. At the beginning of this section of 1.2, we discussed both renewable and non-renewable energy sources. A renewable energy source is a form of energy that is constantly and rapidly replenished by natural processes. Examples of renewable energy sources include biomass, which is the use of a living or once living organism as fuel, hydropower, the energy produced from the movement of water, geothermal, the use of heat from within the earth or from the atmosphere near oceans to warm houses or other buildings, wind, the use of wind to generate electricity, and solar, the use of the sun as a source of heat, for instance, to heat a room within a house. A non-renewable energy source is one that's obtained from the earth as a liquid, gas, or solid and cannot be replenished in a rapid manner. Examples of non-renewable energy sources include petroleum, natural gas, coal, propane, and uranium. I think it's important that all of us know how we use these energy sources to create electrical energy. Let's take a look at a few energy conversions for making electricity. Starting with fossil fuels. Once they are collected, they are transported to the power plant. The fossil fuels are then burned to heat water. When the fossil fuels' many hydrocarbon bonds are broken, they release large amounts of energy. The steam from the water then increases in pressure, forcing a turbine to spin. The turbine is used to rotate a magnet encased in a generator at high speeds. As the magnet spins, electrons are produced and they power the electricity grid. With solar panels, they work by absorbing sunlight with photovoltaic cells, generating direct current energy, and then converting it to usable alternating current energy with the help of an inverter technology. AC energy then flows through the home's electrical panel and it's distributed accordingly. With wind turbines, when the wind blows past a wind turbine, its blades capture the wind's kinetic energy and rotate, turning it into mechanical energy. This rotation turns an internal shaft connected to a gearbox, which increases the speed of rotation by a factor of 100. That spins a generator and produces electricity. With hydroelectric power, specifically at hydropower plants, water is stored in a water reservoir behind a dam, and then it's released by the force of gravity as it flows through a pipe or penstock, then pushes against it and turns blades in a turbine to spin a generator to produce electricity. With nuclear energy, it begins by the splitting of uranium atoms, a process called fission. This generates heat to produce steam, which is used by a turbine generator to generate electricity. With cars, the internal combustion engine in the car converts the potential chemical energy in gasoline and oxygen into thermal energy, which is transformed into the mechanical energy that accelerates the vehicle, increasing its kinetic energy by causing the pressure and performance of the work on the pistons. Other examples of energy transformations include chemical to kinetic, such as food is consumed and it's converted into motion for playing sports or taking rest. Radiant to chemical energy, such as sunlight is consumed by plants and converted into energy for growth. Electrical to thermal energy, such as when energy is transferred to an oven, it's converted to thermal energy for heating our food. In regards to the current energy concerns, the use and cost of energy affects each of us every day of our lives. Many issues arise from the use of energy. Greenhouse gas emissions, acid rain, climate change, dependency on depleting supplies of fossil fuels, especially from politically unstable regions of the world. Today, 80% of the world's electrical production comes from fossil and nuclear fuels, and virtually all transportation is fueled by liquid petroleum or gasoline. The World Energy Council projects primary energy demand will triple by the year 2050 as populations grow to 8 to 9 billion and developing nations elevate living standards. The fossil fuels by definition are non-renewable and are destined to run out at some point, so economies will be forced to change as these fuels are depleted. Rich nations will be insulated a bit longer, yet scarcity will surely create geopolitical tensions. The emissions from the burning of fossil and nuclear fuels create atmospheric, water, and land pollution, as well as toxic waste. The United Nations Intergovernmental Panel on Climate Change, or IPCC, says this combustion is causing a discernible change of the global weather and climate patterns that will affect all of humanity in decades to come. Energy can be defined as the capacity for doing work. The simplest case of mechanical work is when an object is standing still and we force it to move. Work can be defined as transfer of energy. In physics, we say that work is done on an object when you transfer energy to that object. If one object transfers or gives energy to a second object, then the first object does work on the second object. Work is the application of force over a distance. Lifting a weight from the ground and putting it on the shelf is a good example of work. The force is equal to the weight of the object, and the distance is equal to the height of the shelf. Thus, work equals force times parallel distance. Because energy is the capacity to do work, we measure energy and work in the same units, which are Newton meters or joules. And as you can see, 1 joule is equivalent to 1 Newton meter. In this practical example of how to do work, we have a student lifting a 50-pound ball 4 feet in 5 seconds. How many joules of work did the student complete? So again, to calculate work, it's force times parallel distance. So our force was 50 pounds and our distance was 4 feet. So if I multiply 50 pounds by 4 feet, I get 200 foot-pounds. This is an amount of work, but it's not the SI unit for joules. Therefore, we want to know how many joules of work did the student actually complete. So to do this, we need to convert our SI units and then calculate the work. 50 pounds, we're going to change pounds to newtons. So you need to know that 1 newton is equivalent to 0.225 pounds. So if I multiply 50 by 1 over 0.225, I get 222.5 newtons. Then I also need to convert feet to meters. 1 meter is equivalent to 3.28 feet. So I'm going to take my 4 feet, multiply it by 1 meter over 3.28 feet. The feet will cancel out, and I'm left with 1.22 meters. So to calculate work, we'll do force times parallel distance, which would be 222.5 newtons times 1.22 meters, and we get approximately 271 joules. Efficiency is the percentage of the input energy that is transformed to the output energy in a desired form. We refer to efficiency as energy out divided by energy in. Again, efficiency is usually written as a percentage, so we'll take that ratio of energy out over energy in and we'll multiply it by 100%. Most electric power plants and internal combustion engines have an efficiency around 30%. For a coal power plant, for example, 30% of the energy from the coal ends up as electricity. The rest of the energy goes out the smokestack as thermal energy in the flue gas. If the power plant is co-generating, it captures this energy as useful output, heating a building, for example. Then the efficiency can be as high as 80%. In a car engine, the efficiency is also about 30%. Only about 30% of the fuel's energy actually gets to the drivetrain. Power, which uses the symbol P, is the rate at which energy E is expended or work, W, is performed in time T. Power is the work done in a unit of time. In other words, power is the measure of how quickly work can be done. The unit of power is watts. 1 watt is equivalent to 1 joule per second. Both work and watts are abbreviated with a capital letter W. Since the watt is a unit, it will only appear next to a number, whereas work is a variable and only appears with a number if being multiplied by some other quantity. There are many different types of power. Some of these types that we will focus on in this course include electrical, mechanical, and fluid power. Electric power is the rate per unit time at which electrical energy is transferred by an electric circuit. It is the rate of doing work. In terms of an electric circuit, electrical power is the rate per unit time at which electrical energy is transferred by an electric circuit. Mechanical power uses mechanical energy to do linear or rotary work. It can be either kinetic energy, which again is energy in motion, or potential energy, which is stored energy. A moving car possesses mechanical energy due to its motion. A moving baseball possesses mechanical energy due to both its high speed and its vertical position on the ground. A textbook at rest on the top shelf of a locker possesses mechanical energy due to its vertical position above the ground. A barbell lifted up high above a weightlifter's head possesses mechanical energy as well due to its vertical position above the ground. A drawn bow possesses mechanical energy due to its stretched position. And then finally, with fluid power, which we'll discuss more in detail later on in the semester during section 3.2, is the use of fluids under pressure to generate, control, and transmit power. These fluids can be subdivided into liquids for hydraulics or gases for pneumatics. Fluid power is subdivided into hydraulics using a liquid such as oil or water, and pneumatics using a gas such as air or nitrogen. So coming back to our example of a student lifting a 50-pound ball 4 feet in 5 seconds, now we want to know how many watts of power did the student actually use to lift the ball. So recall that the work done was 271 joules. To calculate power, now we're going to take into account time. So it's going to be work divided by time, or 271 joules divided by 5 seconds, which comes out to be 54.3 joules per second, or 54.3 watts.